Having seen in the previous lecture the two somewhat similar techniques of maximum likelihood estimation, maximum a posteriori estimation, which were derived under very different assumptions, but we managed to bring them to common denominator, we'll look at another two techniques which are again somewhat similar. The first of them is least squares, and the second will be the minimum mean square error estimation. As before, one of them is non-Bayesian, the other one is Bayesian. The definition of these estimators are as follows. The least squares estimator is very common for non-random parameters, and the model for it is as follows. Given k, scalar, and in general non-linear measurements, z of j, function of x as follows. There is an h of j and x plus w of j, and the function h is not necessarily linear. We define the least squares estimator for the parameter x as x hat ls based on the k measurements, z of j, j1 from 1 to k, as the argument that minimizes the sum of the squares between the observed values and the values we would observe in the absence of these w's, which are the noises. And that's why it's called least squares. This is a nonlinear least squares problem. In many cases, the function h will be linear in x. Then we can have a linear least squares problem, which actually has a very nice explicit solution and will be discussed in more detail for a vector parameter rather than scalar. Its solution will be also put in a form that you will see later. It's almost identical to the one of the dynamic state estimator, the Kalman filter. Now, the criterion we just presented before, which is the sum of the squares of the errors between the observed values z and the model h, makes no assumption about those measurement errors, the w's, or noises. Now we can do the following. We can model the w's as independent, identically distributed, zero mean Gaussian random variables. So the w's will be Gaussian, mean zero, variance sigma square, IID. Then it turns out that the least squares estimator will be exactly the same as the maximum likelihood, the MLE estimator, under these assumptions. So least squares makes no assumption about the w's, just minimizes the sum of the squares of the w's, which is the deviation between z and h. Now, if we model the w's as Gaussian random variables, we can see in a couple of steps how the LSE, least squares estimator, and the MLE coincide. Specifically, in this case, z of j, that's the measurement, will have mean h and variance sigma squared, because again, z is h plus w, given x, h is deterministic, w are random variables with zero mean, so it shifts the mean of the sum. What is the likelihood function of x? From the k measurements, denoted here as lambda sub k of x, is by definition the PDF of this set of measurements z super k given x, which is the joint PDF of z1 through zk given x, which is the product of Gaussian densities with argument zj, mean h of j and x, and variance sigma squared, which is really a constant, times e to the minus, again another constant, sum zj minus h of j and x squared. So what we have now is in the exponent minus a constant times the sum of the squares of the deviations between the observations and our model h of j and x. And therefore, if you want to maximize the likelihood function, maximize the exponential, amounts to minimizing the exponent because of the negative sign here. So what we really have, the least squares method with supposedly no assumptions about the noises, really is a disguised maximum likelihood assumption, maximum likelihood estimator under specific Gaussian IID assumptions about those same noises. So what we have is a very interesting result that two estimators are very similar again. Now, one more estimator is the minimum mean square error estimator. Remember, the least squares estimator was for non-random parameters. The maximum likelihood estimator was also for non-random parameters. Now we'll go to something that looks somewhat like the least squares, but it will be for random parameters, namely it will be a Bayesian technique. So for random parameters, the counterpart of the least squares estimator will be the so-called minimum mean square error estimator, MMSE, and the x hat MMSE function of z will be argument that minimizes the expected value of the square of the difference between x hat, the estimator to be found, and the random variable x. Now, this is a random parameter, so x is a random variable, and that conditioned on z. Now, the solution to this turns out to be the conditional mean of x given z, e of x given z, will be the x hat MMSE function of z. And the definition of the conditional mean is the integral of minus 2 plus infinity x p of x given z dx. So there is a posterior density. This is now a second way of using the posterior density of the parameter x given z when it is modeled as random. First was the maximum a posteriori, the peak, the mode of the posterior density. Now will be the mean of the posterior density. How do I obtain this? If we take the mean square error as defined a moment ago and take its derivative with respect to x hat and set it to 0, so d to dx hat of the expected value of x hat minus x squared given z, we treat now x hat as a function to be determined. So take a straight derivative with respect to x hat, you end up with a 2 after passing the differentiation inside the expectation, and x hat minus x here conditioned on z, which because x hat will be a function of z, because that's our goal, we will estimate the parameter in terms of z's. Therefore, given z, x hat is not random, but who is random here is this x. So we have 2 x hat minus e of x given z equals 0, and clearly the solution to it is x hat equal the expected value of x given z. We can, having seen the way to obtain the result for a scalar random variable, for a vector random variable, we can obtain the same thing by setting the gradient of the mean of the squared norm. So the minimum of the mean squared error, but it's a vector, we take the norm of the error squared, take the mean and its gradient, the counterpart of the derivative in the multidimensional case. So del sub x hat expected value, this inner product is the squared norm of the error. Remember, the error is x hat minus x, or x minus x hat. It really doesn't matter the sign because this is a square, which gives us, according to the rules we have seen for the vector, this gradient operation, 2x hat minus e of x given z equals 0, which is the same thing as before, except that this is a vector equality as opposed to scalar equality. The notations are the same, but this is a 0 vector. So we have the same result following for the vector case. Now, some examples of least squares estimators. Let's take a simplest case, just one measurement first. Single measurement, unknown parameter x. This measurement is z equal x plus w. The least squares criterion says minimize the square of z minus x, and the resulting argument is the x hat lx, x hat ls. What this is obviously the best value to be chosen for x is z. So we have now the mean square, the least squares estimate in the case of a single measurement equal to the single observation here. Now, this is exactly the same result as the maximum likelihood estimator for the same problem, with w defined in a slightly more elaborate manner as a zero mean Gaussian random variable. And again, this is due to the fact that maximizing the likelihood function, which is Gaussian, is equivalent to minimizing the square in its exponent, which is the least squares criterion. So we have the general proof, and we verify it in this case for the special example. If we have several measurements, k measurements, z of j is x plus w of j, j going from 1 to k. The wj's are independent, identically distributed IID, normal, zero mean with common variance sigma square. The likelihood function, lambda k of x, so this is the likelihood based on k measurements that we have here, is a constant, e to the minus 1 over 2 sigma square, sum zj minus x squared, where j goes from 1 to k. So as before, the maximum likelihood and least squares estimates will coincide, and it can be easily shown that they are given by the following expression, just a little bit of algebra, and handling the exponent, and the x hat ml and the x hat ls both are z bar, the sample average of the z's. So the sum of the z's divided by as many as they are. So this is called the sample mean or sample average. Now, it would be interesting to compare the minimum mean square error estimator and the map estimator in a similar situation, because both are Bayesian, both use a prior. In the single measurement example, with the prior PDF on the parameter that we want to estimate, the posterior was obtained as p of x given z, 1 over root 2 pi sigma 1 e to the x minus psi of z square over 2 sigma 1 square, and this psi was obtained using a prior that was Gaussian, and the mean of it was x0, the variance of it was sigma 0. So, if you are looking for the map estimate, clearly we have shown this was x map psi of z. If you want the minimum mean square estimate, you're looking for the mean of this conditional or posterior density, which happens to be the same psi of z by inspection, because we know this is the term that is the mean in the Gaussian density. So what we have is that x hat MMSE, minimum mean square error estimator, which is the expected value of x given z, is the function psi of z, which is also the maximum a posteriori estimator. So these two coincide. Now, why? The mean and the mode of a Gaussian, remember the Gaussian is symmetric, unimodal has a single maximum, and that maximum happens to be the mean. So the mean and the mode coincide. Therefore, the MMSE and the map estimators are all the same in this Gaussian case. Some of the properties of interest for estimators will be discussed next. First is unbiasedness. How do we define unbiasedness? For a non-random parameter, an estimator is unbiased if the mean of my estimate, and remember the estimate x hat, that's a function, becomes a random variable as soon as we put in the values of z. These are the observations. So what we want is that the expected value of this random variable over all the possible observations should be the same as the true value. So on the average, we got it right. Clearly, the expectation over the estimate, because it's a random variable due to being a function of the measurements, is taken with respect to the conditional PDF, P of the bunch of measurements, given x equal x0. So evaluated, the likelihood function turns out to be, in this case, the density according to which we calculate this expectation. So at the true value of the parameter. In the Bayesian case, if x is random with a prior P of x, you take the average over the estimate, and now the expectation is taken over not only the measurements, but also the various values that this random variable x, the unknown x, can take. So we take an expectation over x and z, and the result should be the mean of x. We can bring these two definitions into a single one by defining the estimation error x tilde as x minus x hat. This is a convenience. We could define it with the x tilde as x hat minus x, but this is more convenient, as you'll see later. So what we say about this error, on the average, the error has to be 0. The expected value of the error has to be 0. So this is unbiasedness. If the property here holds for all k. Now there are some problems, and we'll see one of them at least, where we have this property not satisfied for a finite k, but it is satisfied as k goes to infinity. Namely, an estimator might be only asymptotically unbiased. There might be a typically small deviation, a small bias, if you have a finite number of measurements, but that bias decreases to 0 as the number of measurements goes to infinity. So what this says up to now is, on the average, that's what I get over all the possible measurements. What we are interested in is a little bit more than this. And before proceeding to the second measure of performance for an estimator, we'll look at some examples of estimators which are unbiased now. We'll take the maximum likelihood estimator of the parameter x with true value x0 based on a single measurement, in which case x hat ml is just z, the single measurement, z being x plus w, and w is 0 mean. Then what we get is the expected value of x hat ml, which is the expected value of z, because x hat ml is z, is the expected value of x0 plus w. Now x0 is a fixed number, w is a random variable but has 0 mean. Therefore, the expected value of x hat ml is really x0, in view of the fact that I used, or I modeled my observation as having a 0 mean error in it, a 0 mean noise. there was a slightly more complicated expression for the maximum a posteriori, the map estimate. Remember, that was the linear combination between the prior mean and the observation z. So what we have now is a situation where there is a prior information. There was no prior in the maximum likelihood case, but this is the map case. There is a prior model consisting of a Gaussian model for x with mean x bar and variance sigma 0 square. So you can see again here the fact that the map estimate is a linear combination of the prior mean and the observation with these two coefficients summing up to 1, a weighted average. And if we take the expected value of this weighted average, you can see clearly that x bar is not random, so there's nothing to do with the expectation, but z is a random. And we take the expected value of psi. The first one stays as is. The second one becomes our weighting times the expected value of z. But what is z? Z is really x plus w. What is E of z? Is E of x, which is x bar, plus E of w, which is 0. So once you can see this is 0, you have an x bar here, an x bar here, and now the fact that the two coefficients, that's a linear combination of them, a weighted average, the two coefficients sum up to unity, you end up with x bar. So both these estimates, maximum likelihood and maximum a posteriori, different in nature, are unbiased according to the proper definitions. Now, here's now an example where you can see that it is not true that we can always get unbiased estimators. So, what if I want to estimate two parameters? I have a bunch of random variables. I have k measurements, and there is an unknown mean x of this set of k measurements. And I don't know the variance. So what I measure is a bunch of z's, each equal to x plus a 0 mean noise. So x is the common mean of my z's, because the noises w were 0 mean. So with x being the common mean and the w's being independent, I have the likelihood function as before, but now we are writing the normalization constant explicitly, because we said there are two things we don't know. We don't know x and we don't know sigma. And now we'll use the likelihood equations. There are two of them because there are two parameters, x and sigma. We will set to 0 the derivatives of lambda, or more conveniently of the natural log, ln of lambda, once with respect to x, once with respect to sigma. So here you see the likelihood equations. This function is nice, differentiable, no problem. When we set the partial with respect to x to 0, we have a simple equation, and we can solve it. The partial with respect to sigma requires a little bit more work. So with this equation, that's really the same as we had when x was the only parameter to be estimated. So the solution to the likelihood equation for x will be the same, the sample mean, namely the problem that we have here that yields an estimate of x, an estimate of sigma. You can come up with the same estimate of x regardless of whether you know or you don't know sigma. And the reason for this is that the sigma cancels out in the likelihood, the first of the two likelihood equations, the one for x. The second one has both x and sigma, and there's no more cancellation. So we write the second one, and the result, we put into it the solution, substitute the solution obtained for the first one, and solve for the second one. So the sigma maximum likelihood squared clearly from this equation will be 1 over k sum of zj minus x hat maximum likelihood squared. So this is 1 over k times the sum of the deviations between the observations, sum of the squares, the differences between the observations, and the estimate for the mean. Now, to understand what we have here, we have to substitute the sample mean. Here is x hat ml, which is the same as z bar. This is the sample mean. So we substitute here the sample mean, and this is the expression of the maximum likelihood estimate for the variance. The mean of the estimate of the mean, the average expected value of x hat ml, is clearly going to give you back the correct value x0, because this is just k x zeros plus the noises have zero mean divided by k, so we are back to x0. So the sample mean estimator that we derived is unbiased, both in the cases where the mean is the only parameter to estimate or we estimate mean and variance. There's really no difference. What about the variance? It's a little bit of algebra here. The expected value of the variance estimate. Here's the expression, 1 over k sum z minus vj, 1 over k sum of zi. And I need here a different index, obviously not to be confused. This is a running index in the inside summation, this is for the outside summation. Now, we can substitute and put in the noises. And if you replace z by x0 plus w, because here you have 1 x0, here you have k of them divided by k, the x0 cancels out. So we end up with an expression which depends only on the w's. Now, what do we have here is a w of j, but here you have all the w's from which I will take out the w with the same index as this, which means I modify my sum. First, this k is squared and sent out here. So what I will have here, kwj. But here I have all the w's, including one of them is also wj. So I really have k minus 1 times wj, and here I have all the other w's except for I equal to j. Now we have the ability to square the expression and take the expected value that we have here. So what do I have? We have a k minus 1 squared times the variance of w, j. This appears k times, so there is a k cubed that is cancelled with k squared. Now what do we have here? K minus 1 different w's from I going from 1 to k except the wj. So I have k minus 1 of this, each variance is sigma 0 squared, and absolutely no cross terms. So we separated and have no wj in the summation. These are all different indices, and the single wj is here. Because the w's are zero mean and independent, all the cross terms that we obtain after the squaring will cancel due to the expectation. So what we have here is a k minus 1 squared plus k minus 1. We can factor this out. There's a k here that we end up, and that cancels with this, so we get that the expected value of the variance estimate is k minus 1 over k times the two variance. You can see that for any finite k, this is a little bit biased. Fortunately, the bias goes to 0 as k gets larger and larger. So the sample variance is biased, but asymptotically unbiased. You might be familiar from results from statistics tests where they really prefer not to use the maximum likelihood estimator for the variance, but an unbiased estimator, namely by changing the denominator from the sample variance, which was 1 over k, sum of the squares of the deviations between the observations and the sample mean of the observations, to 1 over k minus 1, the same sum, we end up with an unbiased estimator, and this is the more common sample variance used. But again, for reasonably large k, this is not going to make a big difference. And practically speaking, for small k, I wouldn't try to estimate the variance anyway.